This is on net change and displacement, and this is not in Chapter 6. I've listed it under Chapter 6. It's discussed, it starts actually being discussed back in Chapter 4 when we talked about the second fundamental theorem of calculus, but this is a topic that pops up on the AP, and they don't spend enough time. The examples are kind of sprinkled throughout the textbook, starting back in Chapter 4, Section 4. So we're going to kind of talk a little bit about it. And I also have noticed displacement. Displacement and distance, there's a difference. If you follow, let's say, for example, football, you may see a running back grab the ball and run to the right side of the line, see that he's going to be tackled, so he turns around, he runs to the left side of the line, and you can see that he's going to be tackled over there, so maybe he turns around again and then cuts back through the middle, and he runs and he gets tackled after gaining maybe 2 yards. But he will have ran possibly as much as 50 yards. So the idea here is, what's displacement and what's distance? Displacement is how much he actually, in this case, moves the ball forward from the line of scrimmage, which would be 2 yards. Whereas the distance that he traveled has to do with, going to the right, going to the left, coming back to the middle. It might be 50 yards. So we'll talk a little bit more about that, but distance is kind of like gross, and displacement is kind of like net. And we'll talk a little bit about displacement with this idea of the net change formula. So back in Chapter 4, we introduced the fundamental theorem of calculus, and that was the first fundamental theorem of calculus, again showing how the integral from a to b of lowercase letter f of x dx is equal to f of b minus f of a. If we let lowercase letter f of x equal f prime of x, that means that dy dx is the change in the y with respect to x. So we apply this with the idea of rates, and in this case we'll let t be the independent variable for time, and then s of t might be one quantity that we're measuring as a function of t, whereas if we take the derivative, r of t would be the rate of change. So in a lot of problems they will give us the rate of change of something that's going on, and would not necessarily be an easy problem necessarily to integrate, and sometimes they are, sometimes they aren't, but we can find the change in how things are going, the net change, by taking the integral from a to b of our rate, okay, of change r, and we get this value, this number, the antiderivative of r, which is s of b minus s of a, being the actual net change in our function s that's over the interval from a to b. Let's try a quick example here. I have water flowing into a tank at a rate of r of t, which is t squared cubic feet per minute. How much water flows into the tank over the time interval from 1 minute to 5 minutes? Well, based on what I just said, here's my rate. I am going to integrate. Let me see if I can move this up so you can see it a little bit. I am going to integrate. I want the change in the amount of water that flows in the tank. So here it's at 1 minute, here's at 5 minutes. I want v of 5 minus v of 1. How much water is in the tank after 5 minutes minus how much water was in the tank after 1 minute. Well, this is going to be the integral from 1 to 5 of r of t dt, which is the integral from 1 to 5. R of t is t squared, so t squared dt, which of course is 1/3 t to the third power running from 1 to 5, which would be 125 thirds minus 1/3, 124 thirds. And this would be in cubic feet of water. This would be in cubic feet. So from 1 minute, it's a story problem, I'll write it out. From minute 1 to minute 5, there flows, that's not very good wording, a total of 124 thirds cubic feet, or if you wanted to, that would be 41 1/3 cubic feet of water into the tank. So we used the integration here, the fundamental theorem of calculus, to be able to determine an amount given the rate. So we'll try that here. Let me go ahead and move this. We'll actually get to some kind of a displacement problem. Let's see what we can do here. Find the displacement of an object moving in a straight line over a certain interval of time. Now, if it's moving over a straight line, let's say it's a horizontal line, it might move to the right, and then it might move back to the left, and then it might move back to the right, it might move back to the left. Just like the running back going to the right or to the left, the displacement is actually the net distance that the object moved from its starting point to wherever its stopping point is. So we can find that the displacement of an object along a straight line over a certain interval of time. Here's my rate. I integrate from A to B. That would be the times. That's the interval of time. And of course, that's S of B minus S of A, whereas prime of t is the velocity. So if I have the velocity, if I have the rate, in this case 16t e to the opposite t squared minus 1, what is the displacement of the object over the interval from 0 to 2? Well, that was going to be, what should I use here? Let's say S of, going from S of 2 minus S of 0 here. So that's going to be from 0 to 2 of my velocity. So from 0 to 2 of, what was that, 16t e to the opposite of t squared minus 1 dt. Well, I don't need a 16, I need a negative 2 there. So I'll rewrite this as negative 8, the integral from 0 to 2 of negative 2t e to the opposite of t squared minus 1 dt. Now that I can integrate, so this is negative 8. The first part here, it's going to go to e to the t, so, or e to the u in this case, so that would be e to the opposite of t squared, and then minus, I've got the 8 here, the negative 8 here times the integral, let's see, the integral of that would be opposite of t. So how do I want to write this? I've got I got a negative out in front, and it's, let's see here, that's a minus here, so I'm going to write the negative 8 times the opposite of t running from 0 to 2 and from 0 to 2. I guess I could have written that all a little bit differently here. So this is, if I plug 2 in, I get e to the negative 4 minus 1. So that's negative 8 times e to the negative 4 minus 1. And 3 negatives minus, plug in 2 and plug in 0, I would get 2 minus 0, because this negative and this negative kind of cancel one another out, so that's this negative right here. So I end up with a real mess here. So this is going to be negative 8 over e to the 4th. That's going to be plus 8 minus 2 is going to be plus 6, which is approximately 5.853. Now I didn't do that in my head. I wrote that down on a piece of paper so I could remember it. And this would be, let's see, well, there are no units given, so this might be in inches, feet, whatever the units are of measure. Okay? Now, I'm going to use this same example here, if I'm not mistaken, in this one. It's been a while since I set this kind of up. It says, if we say for this example, the initial position of the object was at x equals negative 1. So back here, the initial position was at negative 1. Then x of 2 would be negative 1 plus that an amount to be 4.853 units. So it gives us the buildup from wherever we started at, and in this case we started at 0 here, because if you plug 0 in here you get negative 1. If you plug 0 in here you get the negative 1. So that's where we're going to come up with this amount. Now, an object moves along the x-axis, so we're still doing that same style of problem here, and we're going to let x of t be the position at time t. All right, so we've got v of t is equal to x prime of t. It's the derivative. This is the position, this is the rate, the velocity be the velocity at time t, and we're going to let the absolute value of the velocity be the speed at any particular time t. So I'm going to move this up. X of b minus x of a is the integral from a to b of v of t dt. It's the change in the position over the time interval from a to b. All right, that's the change in position. That's the displacement. Okay, the absolute value of this from a to b is going to be the total distance. So this is displacement, and this is going to be the distance right here, the total distance. Now look at the example. I drew my curve, some above and some below, and the area of this region above is A, and the area of this region below here is B. Now what does that tell me? That tells me that if I'm integrating the velocity, I'm looking at the area under the curve. The displacement would be this amount minus this amount, because this amount is going to be negative. It's underneath the x-axis. But the total distance is going to be this amount plus this amount here, thinking of this as a positive amount. A is moving to the right, B is moving to the left. Kind of some wild stuff here. You got to think about this a little bit. So let's try it with an example. If the velocity in meters per second of an object is given by v of t equals t squared minus 2t. Find the displacement and the total distance traveled over the interval from 0 to 5, where t is in seconds. All right, so I want to figure out what the displacement is first. All right, the displacement would be from 0 to 5 of my velocity, t squared minus 2t dt, which is 1/3 t to the third minus t to the second, running from 0 to 5. So that's what, 125 thirds minus 25 minus 0. And see, that'd be 75, so that'd be 50 thirds meters. So that's the change in that it's a positive amount here, that we would have a total gain here of 50 thirds meters from the initial starting point. Now, to figure out the distance, I'm going to have to break this apart, because my velocity back here, remember we're going from 0 to 5. If you plug 0 in, you're going to get 0, but if you plug 1 in, you get negative. You plug 4 in, you get a positive. So this thing is negative from 0 to 2, and it's positive from 2 to 5. So what I'm going to have to do is I'm going to have to break this into two integrals. I'm going to have to integrate from 0 to 2 of the velocity, the absolute value of the velocity. And then I'm going to also have to integrate this from 2 to 5 of the absolute value of the velocity. Now, which one's which? Well, in this case, from 0 to 2, it's negative. This is negative, so I want to take the opposite of this. This is going to be from 0 to 2. The opposite of t squared minus 2t is 2t minus t squared. And that's with respect to plus the integral from 2 to 5. And here it's positive, so that's just the t squared minus 2t dt. Now, you can go through the calculations. It's a little messy, but you're going to end up with 58 thirds meters. So you can see that there's actually a gain here in distance, because some of it was to the left as compared to some of it being to the right. If you were to try to kind of sketch this, just to get a kind of a rough idea of what's going on, and this is going to be really, really rough here, because I'm not going to have a good scale most likely here. I don't know. I think it's pretty big. Let's make these 5. And then this is from 1, 2, 3, 4, 5. What happens here is that my curve starts down here. That's this curve right here. That's the velocity curve. And then it goes up here. Let's see. By the time I hit 5, about 15 there. So it's going to kind of go like this. Okay, and this is 5 here. So I've got this little bit to the left, and then I've got all this to the right. That's why they're so very close. This one being just a little bit more. This is the distance to the left, and this right here would be the distance to the right. This being your x-axis and such. All right. Now I have one last example that I want to go through, and then we'll call it quits here as far as this section. And actually, with respect to the videos for each section, this is the last video. So it's time to take a sip of coffee and reflect. Ah, what a weird, wonderful ride it's been. Suppose that people visiting an amusement park enter the park gate at a rate of R of t equals -4 times quantity t minus 8 quantity to the third power, where R of t is the rate in which people per hour and t is the time in hours since the park opened. Determine the number of hours t it will take for the number of people, capital P, for that's the total, that's the integral P, to reach 2,000 people in the park. Well, I don't know. If the park opens at 0, I don't know what time, so I'll call it x. And because I'm calling it x, I'm going to write my rate here, my R of t, which is -4 times the quantity t minus 8 to the third power dx here. And of course, this is going to be p of whatever my x value is here minus p of 0. So let's see what we get here. This is going to be up to 4 over 4. I got a -4 there. So this is the opposite of t minus 8 to the fourth power running from 0 to x. So this is the opposite, let's see, x minus 8 to the fourth minus the quantity 0 minus 8 to the fourth. What a mess this is. And I want to know when this is 2,000, so I'm going to set all of this equal to 2,000. So that gives me the opposite of x minus 8 to the fourth power minus, let's see, that's, or hang on a second here. Oh, I have a negative there, so that's going to actually be, because of the negative, this is actually going to be plus. I didn't think that looked right. 8 to the fourth, that's 4,096, and that's got to equal 2,000. The opposite of x minus 8 to the fourth equals -2,096. X minus 8 to the fourth equals positive 2,096. Take the fourth root. Now I'm going to pick up a plus or minus here on this, but it won't make sense if it turns out to be a negative number here because it's a time. But I'm going to go ahead and write plus or minus the square root of 2,096, and anyway I get x minus 8 is equal to plus or minus, actually the fourth root, excuse me, not the square root, the fourth root of 2,096. And when I did this prior, working this problem out, I received two values, 1.234 and 14.766. Now it says here, determine the number of hours it will take for the people to first reach 2,000, because what happens is after a little more than an hour, because this is in hours, it reaches 2,000, it increases, and then it starts to drop back down as the day wears on, so that almost 15 hours after it opens, it's back down to 2,000. So this is 1.234. This is the first time, when it first reaches that. So that's what, 1 hour and about 14 minutes. If I'm not mistaken. So the park will first reach 2,000 people, 2,000 attendees or whatever, at approximately, see, it opened at, does it say when it opens? It does not say when it opens. At approximately 1 hour 14 minutes after the gates are open. So if it opens, let's say it opens at 8 o'clock in the morning, then it would be 9:14. If it opened at 9 o'clock, it would be 10:14, and so on. And we've answered that problem. Now there's a wide mix of these problems, and the reason I took the time to go over this is because there's inevitably some type of a problem that involves a rate on the free response part of the AP test. So I want you to practice these, and you'll see these as we're going through some of the different practice problems. But as always, practice, practice, practice.